An application of first-order differential equations are what are known as mixture problems. So mixture problems are, well, they basically happen in some sort of container. We typically, in a first-level differential equations class, think of a tank. Okay, so you've got this situation where you've got some sort of tank, and you can think of it as small or as big as you want to, and it's got some stuff flowing into it, and it may or may not have some stuff flowing out of it. And I guess may or may not have stuff flowing into it also works. Okay, so it depends on your situation. The situation that we're going to see will often have both your solution flowing in as well as flowing out of the tank. So the idea goes as follows. You've got a tank that has maybe some sort of wheel or paddle on the inside that's continuously mixing up all of the stuff. Classic first example is something like salt water. So you've got this brine, you've got this solution where you've got your pure water, you've got your solute, that's your salt, and it's continuously mixing inside of the tank, so you actually do have fully mixed in salt or salty, briny water. Okay, maybe flowing into the tank, you have fresh water, and flowing out would be whatever the well-mixed solution would be. So if you started off and it's pretty salty and you're pushing fresh water in, after a certain amount of time, the solution is going to be diluted so much that the amount of solute, the amount of salt inside of this tank, inside of this location right here, is going to be essentially negligible. So maybe you're cleaning the tank, say, and you want to know, all right, well, how much time will pass when we get down to no salt in the tank? In reality, that's probably going to turn into a limit, but maybe you say, all right, how about I get down to a certain concentration of salt, like 1 part per million or something. Okay, so that's the situation that we're going to be looking at here, is some sort of something coming in that is either a mixture or has none of the solute coming in, some sort of mixture in here where it's all getting mixed up together, and something leaving. You can actually have multiple things flowing in, you can have multiple things flowing out, you can have nothing flowing in, and then you look to see when the tank completely drains. So there's lots of scenarios that you can do. But this is the base case that all of them work off of. So let's see how you deal with that base case. Okay, so in terms of what flows in, the flow rate coming in is in symbol given by R with a subscript I here for in. I'm going to put units here, but in our examples, these units can totally change. It's going to be some sort of volume unit. I did a liter here, and then over some sort of time unit, I went ahead and did seconds here, although I believe my first example has different units. Okay. Now, we're also going to know for the stuff coming in, we're going to know the concentration of the solute that we care about. So if the solute was salt, we'll know the concentration of salt in the mixture coming in. Okay. And that's given by C with a subscript I. Again, I for in, what's coming in, C for concentration here. And notice here in terms of the units, this is the unit of whatever the solute is, and then divided by a volume unit. Now in terms of the outflow, so this is what's leaving your tank, you also have a flow rate. This is an O for out, and again it's volume unit per time unit. And you'll also have a concentration that's coming out, and this is a CO here, again, O for out, C for concentration. Please note this concentration, since we are assuming well-mixed solution, is the exact same concentration as what is inside the tank. So while the rate at which the flow is coming in or out and the concentration of the solute on the mixture coming in or solution coming in is known, these are typically all constants. CO right here, or concentration going out, flowing out, is something that we'd actually are going to have to solve for, or build a formula for, I should say. Now, the volume of the tank, or volume of the solution in the tank at any specific time in t, is given by V, or V of t if you want to be very proper here. And how you build this formula is, it's the initial volume of the solution in the tank, and that should be given to you, whether it's full, whether it's empty, whether it's somewhere in between. And then the new amount of volume coming in is the rate at which the flow is entering, subtract the rate at which the solution is leaving. So you'll look at the difference between the two rates. Notice if there's more stuff coming in than leaving, your volume is going to get progressively more. And if there's more stuff leaving than coming in, your volume will get progressively less. It'll start draining. And if they're actually equal, that's the best case scenario in terms of the differential equation we'll be building. This whole term will zero out because if they're equal, this will go away and the volume will stay constant. Now, the thing that we're actually going to solve in our differential equation given by x of t is the amount of solute in your tank. So if you're dealing with brine or salt water, the solute would be that salt. Okay, so it's whatever the stuff is it's being mixed in to make your solution. Our concentration of the solute in your solution at any time, that C of O, that thing I said that we were going to build a formula for, this is given by its total amount of the solute in the tank divided by the total volume in the tank at that same time. So notice x divided by v. Both of these are functions with respect to time. So this guy, this concentration, is also going to be a function with respect to time. Please note there are times when the amount of solution coming in, the amount of solution going out, depending on the concentration. If the concentration coming in matches the concentration that's already in the tank, you won't have any change in what's going on with your mixture, and the concentration flowing out will be the same as the concentration flowing in. That is actually really rare for us to see. Most of the time there's going to be some sort of change here. Now, in terms of figuring out the differential equation, if you're looking at the rate of change of your solute in your tank at any particular time, that's going to be the rate of the stuff coming in versus the stuff going out, where rate here is specifically our flow rate times our concentration, okay? So watch out, rate in minus rate out is not Ri minus Ro. It's actually these guys multiplied together, so flow rate times concentration, flow rate times concentration. So watch out for that. So in symbol form, let me actually write this in symbol form. This is dx over dt equals rate in to concentration in minus rate out, concentration out. That's the formula you need to know. The other formulas you need to know are those two guys, okay? If you know those three formulas, you can get through any of these mixture problems, no worries. So let's actually look at an example. So suppose you have this example, and it's a nice story problem here. We've got a 400-gallon tank that initially contains 100 gallons of brine, so remember brine is salt water, containing 50 pounds of salt. So brine, or salt water, containing 1 pound of salt per gallon, enters the tank at a rate of 5 gallons per second. So this is your rate, your flow rate. And the well-mixed solution, so remember it's mixing all together, so no salt falling to the bottom of the tank. The well-mixed solution in the tank flows out at a rate of 3 gallons per second. Okay? So what we want to do is we want to know how much salt is going to be in the tank when the tank is completely full. Because notice the flow rate coming in is 5 gallons per second and the flow rate leaving the tank is 3 gallons per second. So this tank is progressively getting fuller and fuller. First thing I would recommend doing is drawing a picture and setting up your initial value problem. This is the most important thing that you can do for these problems. And often in the past, sometimes when I give people these problems, the only thing I'll ask them to do is go ahead and set up the initial value problem. Okay. So I always like to draw a picture because pictures have a tendency to focus people. Pictures have a tendency to make you think about what's going on, and pictures are just nice. Okay. So I've got this nice little tank problem. I went ahead and labeled flow in, concentration in, flow out, concentration out, and then X here is representing the amount of salt in the tank. So X amount of salt in the tank. In terms of initial conditions, we're told that initially we've got 100 gallons of brine, and those 100 gallons of brine have 50 pounds of salt. Remember, brine in here, our solute is going to be salt. So at the initial time, we've got the 50 pounds of salt. Okay. We've also got, that's a 40-gallon tank, but that's really going to be our end point. Okay. Now, in terms of our rates, rate in is going to be our 5 gallons per second. Our concentration coming in. So there's our 1 pound of salt per gallon. And our rate out, there's our 3 gallons per second. Now, notice we've dealt with this 1 pound of salt. We've got with the 5 gallons per second, 3 gallons per second, 50 pounds. So the only thing that we haven't dealt with in terms of numbers are these square guys. So the 50 gallons and the 100 gallons. So notice both of them deal with volume in the tank. That 100 gallons is going to be your initial volume, so V of 0. And 400 gallons of tank is going to tell you when you're full. So that's going to be, we want to find time when volume is 400. Okay. So let's go ahead and finish this off in terms of the things that we can grab. Our concentration going out is not a number that's known to us. It's always going to be a formula. So this is our X divided by our volume. Note what we still need. We need that volume formula. So volume, we said the formula was initial volume plus the difference in the rates of your solution flowing in and out of the tank times T. Well, we know the different rates. That's 5 and that's 3. So we'll subtract 5 and 3 and get 2. And we have the initial volume of the 100. So this will tell us that our volume formula is 100 plus 2T. Up to you if you want to put the units on there or not. That's not something I worry about as long as you make sure all the units work at the beginning. Okay. Now, what does this tell you? This tells you that we now have a formula for concentration leaving the tank, which would be X. Still don't know X. That's the thing you'd solve the differential equation for. But now divided by volume, and we now know volume is 100 plus 2T. So, grabbing our balancing rule that we had before, this is the formula that gives you your differential equation. So it says your differential equation is derivative of X, so the rate of change of the salt in the tank is going to be the flow rate in times the concentration in minus flow rate out, concentration out. So we plug in, and this first guy, rate in is 5, concentration in is 1, rate out is 3, concentration out is X over 100 plus 2T. Okay. Simplify it up a little bit as needed. We'll put the 3 and the X both on top here, and the 5 and the 1 will just be the 5 and the 1. Okay. This now is our differential equation, and the initial value for that differential equation, or the initial condition, is right up there with that very first guy we grabbed. So let's solve this. Okay, so at this point, we've built our own initial value problem, and to solve it, we're going to put it in standard form. Okay, so for this guy, you actually have, for this one here, it is a linear form. For mixture problems, and I'm going to go ahead and write this down, mixture problems are either linear first order or separable first order. Okay. And it all depends on the following. It all depends on how that concentration flowing out formula lives. So whether it has a T involved, whether it doesn't have a T involved, etc. So that they're either going to be linear or separable or both, and it's perfectly fine if they're both. So in order to get ourselves in the standard form for a linear differential equation, we can go ahead and move this term with the x's over to the other side. We'll find our integrating factor, and our integrating factor here is going to be dealt with our p term. So we'll take the antiderivative, or the integral of that guy. Now this guy here is a fraction, so standard with fractions is to go ahead and look for a substitution. Substitution looks like it should be the denominator, so 100 plus 2t. Let's check that. So if we take this derivative, it's 2 dt. We don't have a 2, so we'll pull the 2 out front, which means when we go ahead and calculate this guy, we're going to get a 3 over 2 integral of 1 over u du. So 3 over 2 natural log of u. And now we just got to put the u back in. Now notice this is the same trick we had before, where we have a log and an e. We've had this several times now. We'll pull the coefficient of the 2 over 3 in as an exponent. Then the e and the natural log will cancel. So this will turn into simply 100 plus 2t all raised to that 3/2 power. At this point, we'll multiply our integrating factor through by our differential equation. And I went ahead and skipped a step. When you multiply through this guy by your differential equation, you actually have a middle step right in here where you've got your integrating factor times your derivative, integrating factor times the term with the x in it, and then you collapse it just because we've done that several times now, I'll go ahead and simplify to integrating factor times your dependent variable. You take the derivative is what you should be at on the left-hand side. Right-hand side is simply going to be 5 times your integrating factor, which is what we've got on that right-hand side. Next step is we'll go ahead and integrate both sides. So if we integrate both sides, we have the integral of the derivative of all of this. We'll integrate the 5, 100, 2t, 3 halves dt. Over here on this side, on the left-hand side, we'll have the integrating factor times x. On the right-hand side, this will actually be a substitution again. And if we have a substitution again, what's going to happen? We'll get 100 plus 2t. We'll get 5 halves out front. We'll have 5. We'll have 2 halves. And we'll have a 1 half. So that all this stuff in the front should cancel. We should have a plus c out at the end. And we should have the integrating factor of 100 plus 2t raised to the 3 halves times x. Now, when we divide through to solve for x, we should then have 100 plus 2t. Notice the exponents will cancel, so that will just be an exponent of 1 plus c times 100 plus 2t raised to the negative 3 halves. And if you prefer to have that in fractional form, that's totally fine. We then solve for c, and you solve for c with plugging in t equals 0, x equals 50. And notice here that c turned out to be 50,000. It's pretty large. Okay. Now, at this point in time, we still haven't actually answered the question, because the question wanted to know what's going on with the concentration when the tank is full. We don't even know when the tank is full yet. So let's go ahead and figure this out. So write down what we've got so far. We've got our solution, specifically how much salt is in the tank at whatever time we care about. Now, when the tank is full, we know that the maximum volume of our tank is 400. Okay? We have a formula for volume. Volume was given by 100 plus 2t. So you just set that equal to 400. Notice we could have done this before we'd done anything with our derivatives or differential equations. So we'll subtract 100 from both sides, we'll divide by 2 on both sides, and what you'll get is you'll end up with t equals 150. So this tells us that after 150 seconds, your tank is going to be full. Now, at this point, we're ready to start thinking about concentration. Okay? So how much salt is in the tank when it's full of brine? Well, that's just, we're going to plug 150 into this formula. I just plugged 150 in for t in this formula, plugged it into my calculator, and I got back 393.75 pounds of salt was in the tank when it was full. Now, that's not concentration. That's how much salt was actually in the tank. Okay? Now, remember what concentration was. The formula for concentration was the amount of salt in the tank divided by how much solution was in the tank. In other words, you take your formula for x, plug in 150, you take your formula for volume, and you plug in 150, but we've already done that. We know our tank is full at 400, and we know the amount of salt in the tank when it's full is this 393.75. So at this point, I just plugged that into a calculator and got back the decimal of 0.984375 pounds per gallon. And this tells you what the concentration of salt is in the tank when it gets to be full. Okay? And that's the basic idea of one of the things that you can do with mixture problems, crash course of setting up with all the different variables and walking through it. I realized that while we walked through this example, we did skip through some of the algebra and plugging in, but I am assuming that you're okay with filling in those blanks, at least for right now.